So, how does one observe that the metric, Rindler metric, ds squared, which is rho squared d tau squared minus d rho squared minus is not, the Rindler spacetime is not singular at rho equals to 0. One just makes a transformation from this metric to the Minkowskian one, to another coordinate patch. And in this metric, this region is absolutely regular. Similarly, one considers, if one considers two-dimensional line element, which is dr squared plus r squared d phi squared, how does one see that there is nothing bad happening at r equals to 0? One makes, again, coordinate transformation to dx squared dy squared, where this point is not bad. So we're going to do the same for the Schwarzschild metric. So let us consider the Schwarzschild metric. ds squared equals to 1 minus rg divided by r, dt squared minus dr squared divided 1 minus rg divided by r minus r squared d omega squared. So let us make coordinate transformation. To do that, let us represent this metric. We continue this equality. Represent this metric as 1 minus rg divided by r times dt squared minus dr squared 1 minus rg divided by r squared minus r squared d omega squared. And let us denote this part as dr star. So dr star is equal to dr divided 1 minus r g divided by r. So this is so-called tortoise coordinate. Tortoise coordinate. So integration of this equation makes it that r star is equal to r plus rg times log r divided by rg minus 1. And we have fixed the integration constant in this equality such that the relation is like this between r star and r, tortoise coordinate r star. And one can easily see that as r goes to infinity, r star is approximately equal to r and also goes to plus infinity. And as r goes to rg, r star goes to minus infinity because this log goes to minus infinity. So with this choice, this is equal to 1 minus rg divided by r dt squared minus dr star squared minus r squared d omega squared. So, and let us introduce new coordinate v, which is t plus r star. And let us make a transformation from tr to vr coordinates. If one makes this coordinate transformation, to this v, then this metric acquires so-called ingoing Eddington-Finkelstein coordinates. So these are called Eddington-Finkelstein coordinates. And the metric acquires the following form. It becomes like this: 1 minus rg divided by r dv squared minus 2 dv dr minus r squared d omega squared. So despite the fact that now in these coordinates, despite the fact that as r goes to rg, this guy goes to 0, this expression goes to 0, but because this metric is non-diagonal, so this part of the metric is like this, so one can perfectly go with this type of coordinates, so I can perfectly go beyond the region r equals rg. So while the original coordinates are applicable only for r greater than rg, only for this case, these coordinates are already applicable for any r, for r greater than 0. But let us stress that in these new coordinates, that invariant r mu nu alpha beta, r mu nu alpha beta has the same form, and I remind you that it's proportional to some power of rg divided by r to the 6th power, and this guy blows up, goes to infinity when r goes to 0. So the space-time, so while r equals to rg is a singularity only of this metric, but there is nothing bad happening in space-time at r equals to rg, there is a blow-up of the invariant at r equals to 0. So this is a physical singularity already, physical singularity, because Riemann tensor measures tidal forces, the strengths of tidal forces, and they become enormous as r goes to 0. And that's the reason that the space-time, that this metric is applicable only beyond this point. Moreover, one can say that Einstein's theory, Einstein's general relativity, is not applicable as r goes to 0 anymore, because like higher terms in powers of curvature are becoming relevant, so the curvature becomes strong. And Einstein's theory on general grounds can be expected to be applicable only if curvature is small, sufficiently small. So now let us draw light-like geodesics, for this metric. So we want to write light-like geodesics for this metric, radial light-like geodesics. So such geodesics for which d theta is equal to d phi equals to 0, and also ds squared is equal to 0. Then, if for light-like geodesics, this is the law of motion, and we obtain the following equation, that 1 minus rg divided by r dv minus 2 dr multiplied by dv is equal to 0. As a result, we obtain two equations. Either dv is equal to 0 or 1 minus rg divided by r times dv equals to 2 dr. So these are two equations that specifying light-like geodesics. So this geodesic is ingoing because one can notice that this is the equation t plus r star equals to constant, because v is this. As t is increasing, r goes to minus infinity. So this means that this is ingoing geodesic. And this is outgoing geodesics, but one can easily see that these geodesics are actually... So we have the following picture. Let us draw these geodesics. Basically, we have this v coordinate, and we have this r coordinate, and we encounter the following situation, that there is a line corresponding to r equals rg, for which case dv is equal to 0, or dr equals to 0. So this is this geodesic. Then we have these geodesics ingoing. This the ingoing geodesics. And when r is greater than rg, we encounter these geodesics, which are going like this. These are solutions of this equation. These are outgoing geodesics. And then there is a funny thing that when r is less than rg, this equation gives us another type of geodesics, which are outgoing, but at the same time they are going to r equals to 0. And only at r equals to rg we have a vertical geodesic. So this is a picture we encounter for light-like geodesics in the space-time under consideration. Now, this is already the picture that describes a black hole. Why it describes a black hole, why this is a black hole, and why it's so special with this solution of Einstein equation, we're going to continue our discussion in the next lectures.